All right, so we're looking at related rates here. So I'm just going to start with the question and then we will talk through sort of the way to solve these. So a 5 metre ladder rests against a vertical wall at point B. Its feet are at point A on horizontal ground. The feet on the ground slip, and at the instant when they are 3 metres from the wall, they are moving at 10 metres per second. At what speed is the other end of the ladder moving this instant? So if I was to consider this, I'm just going to start. I'm going to put let's just set up our scenario. So we've got our floor, and let's just do a wall like this, and I guess we'll highlight. Okay, and we'll make this the wall here. So we've got this scenario. Now, I'm just doing this so we can talk through it. So let's just copy this down a little bit. I'm just going to line a few of these up so we can talk about it. So we've got 4 of these, and the reason I've picked 4 is because there's 4 easy measurements that I can do. So the ladder's 5 metres. So if we think about, I'm going to do these first 2. So if the ladder's 4 up and 3 across, this would be our ladder, and this is 5 metres here. So the blue represents our ladder. And then I'm just going to pick on the next one. I'm going to go 3 and then 4 out. And that's our ladder there, which is our 5 metre ladder. And then when it finally, you'll notice here that this is 4 up the wall, this is 3 up the wall. And then let's just do our final scenario is straight along the bottom here. The ladder is 5 metres along the bottom and it's lying flat. Or we can go at the top here, we would go that this is conveniently straight up here. Now, our problem states that we've got B here, B here, B here, and then B at this last one is on the ground, and the feet of the ladder is at A, and A. Okay, now, hopefully we can sort of recognise this is a Pythagoras' theorem question. So I'm going to, let's actually go to our steps for related rates, because this is from the text. I'm just sort of doing this so we can go through at the same time and talk about it. So our first step here is draw a large clear diagram. Sometimes more will help. I've done a few. I'm going to use this one as our main one because it makes life a bit easier. Okay. And then write down information on the label. We've got everything we want out of here. We now need to come up with a couple of variables. And so in this space here, let's just pick X because it's horizontal. So we'll do this as an X and we'll do this as a Y. And if we are to consider this scenario, this B value here is our distance of here, of this, it's Y represents the height up the wall, okay? And in this space, X is the distance from the wall. Now, if we were to consider taking the derivative of these with respect to time, so height, so hang on a sec, let's just continue. Sorry, I'm getting ahead of myself. We should follow the instructions. So we write down the information and we've labelled the diagram. We've come up with some values here. We've got Y and we've got an X there as well. So Y is the height and X is that value. Okay, and then we've got to write down an equation that connects them. So we should be able to see here that this is actually a Pythagorean triangle. So if we were to relate these variables, we would go, well, it's a right angle triangle, x squared plus y squared equals 5 squared. That's our ratio. And then our next step here, now we've got this all sorted, we differentiate the equation with respect to time t. So our next step here is we're going to take this equation. So we had x squared plus y squared equals 5 squared. And we're going to differentiate with respect to t. So we're going to, I'll just zoom in a little bit so we can just focus on this. So this means we're going to go, well, with respect to t, we've got x squared plus y squared equals the derivative with respect to t of 5 squared. Now, in this space here, we should obviously look at this and go, well, the derivative of x is 2x, but because this doesn't have a t in it. We're doing implicit differentiation. So we're going to go, well, this is dx dt. Okay, and then our next one here, we've got, well, this is going to be 2y, but we've also got dy dt now because we don't have this isn't, the variable is not t, it's something else. So we've taken the derivative of y with respect to t in that space. And then the derivative of this last one is just a constant, so it's going to equal 0. Now, we've now got these values here of dx dt and dy dt. Now, in this question, what it sort of talks about is we're talking about the change of y with respect to time and the change of x with respect to time. So you've got to remember this is a ladder falling down a wall. And we notice here that if the feet are 3 meters from the wall, they are moving at 10 meters per second. So you'll notice here that I've actually done this, because it's a Pythagorean triangle, this is actually drawn to scale, and this particular diagram here would be 3 meters on the bottom. So if I put this in here, this would be x equals 3 meters, and this would be x equals 4 meters. Okay, now you could solve that by subbing in values and solving the equation. So at the moment we know that if x equals 3, then y equals 4. And we've also been told when x equals 3, we've found out here that when the feet on the ground slip and at the instant when they're 3 meters from the wall, they're moving at 10 meters per second. So this means that as they kick out here, so you've got to remember that these feet here, I don't know whether, maybe I should pick a different color for the speed. This actually has this dx dt of 10 meters per second, and that positive sign actually means moving to the left. So it's a counterintuitive to how we'd usually set it up, and as long as our reference points are correct, it'll all work. And so we've got here dx dt equals 10. Now, all we've got to do now is we've got to sub our values in here, and we can go, well, 2 times 3, okay, because x is 3, and then dx dt equals 10. We've got 10 plus 2, and y was 4, dy dt, all equals 0, which means 3 times 10 is 30, times 2 is 60. So we're going to have 8 dy dt equals negative 30. Okay, we can now divide both sides by 8, and we get dy dt equals negative 30 on 8, which if we half both of them is negative 15 on 4. So that allows us to then, what is the speed at the other end of the ladder moving? So we're looking at, if this ladder is falling out here, this one's falling down, and we can see here it's falling at 15.4 meters per second. So if we write that, the top of the ladder is falling at negative 15 on 4. I think we've got an issue here, that this is not the number I would expect. D4, 8, 15, 15 of, because I've got that, I think it's meant to be 7.5, and I've got this as less than that. What are we meant to be looking at? What error have I made? Rates and differential equations. So 2 times 4. 30 on, why have they got 30 on 4? Oh, this is meant to be 60. I've stuffed up with my multiplication. That should be 60, which then equates to negative 60 on 8, which is negative 30 on 4, which equals negative 7.5 meters per second, because they're the units we've used. The top of the ladder is falling at 7.5 meters per second. Now, the reference of that is the negative sign here represents going down here. So depending on your diagram, you've got to make sure you pick the directions for yourself in those that make sense in the context of the problem, and then double check that it makes sense in the context of the problem. But that's the end of that problem there. Thanks, guys.